Section 22, approximating the area under a curve. So we do this two ways. One way we use trapezoids, and one way we use rectangles. Rectangles is called Riemann sums. Trapezoid is called trapezoidal. So they could have called it rectangle sums, but some guy figured this out, so we call it Riemann sums. Riemann sums can be calculated 5 different ways. One where we choose the left value on the graph, one where we choose the right value on the interval on the graph, one where we use the midpoint, over approximation, and under approximation. We're going to do an example of each of these below. The other way is trapezoidal sums, where we take an interval and we take the two different y values and we average them and then use that as the find the area of the trapezoid to approximate the area under the curve. Trapezoidal sums tend to be more accurate than rectangles, but rectangles are easier to solve, so rectangles are more commonly used in computer applications, which is this approximating way, and why we learned it in here and why it's important is the way most computers solve these problems. Most computers can't do algebra, like the calculators in here, unless you have a CAS, can't do the algebra, and so it just approximates by making tons of rectangles. So let's just hop straight into it and check out our example here. So in this example, we're making trapezoids. We're making 3 of them. It gives us the intervals that we want to use here. Like, we're only figuring out the area from 1 to 16, so we're actually starting right there. And so our first trapezoid has a height of 1 on its left side and a height of 2 on its right side, which I could also get from the chart, 1 and 2 there. It's also 1, 2, 3. Whoops. It's only 3 wide because it only goes to 4, so that line is wrong there. Let me fix that. So it's only 3 wide. So it's 3 wide and it has 1 and 2 on each side. To find the area of trapezoids, you average their heights. Halfway between 1 and 2 is 1.5. And 1.5 times 3 is 4.5, and so that's the area on that interval. On our second interval, we're going from 4 to 9. That's 5 across. And our height on this side is 2, our height on this side is 3, so our average height is 2.5, and so we do 2.5 times 5, and we get 12.5. On our third interval they give us in this problem, we're going from 9 to 16, that's 7 across. We have a height of 3 on this side, a height of 4 on this side, so the average is 3.5. And so we just do 3.5 times 7, and we get 24.5. And you just add all these pieces up, and you get that from 1 to 16, the area under this curve is approximately 1.5 units squared. That's kind of the gist of this, is you're just finding approximations. You're just adding up all the areas of shapes that kind of approximate what's going on here. So now we're going to do this deal with left Riemann sums. So if I always pick the left value and make a rectangle, I'm making these short rectangles because they're always going to under approximate here. If I drew a line straight across, picking the left value on the interval as my value for the entire interval, it's always going to be under approximating. So we should get less for this under this method. So our first height is 1, and our first width is 3, so that rectangle would have an area of 3. Our second height is 2, because we're picking the left value here, which is 2, and its width is 5, so we do 2 times 5 and we get 15, or 10 rather. And our third interval is this big one. It's 7 wide, and we're using the left value, which is 3 as our height, so 3 times 7 is 21. And so our approximation for this interval is 3 plus 10 is 13, plus 21 is 34 units squared, and so yeah, definitely an under approximation. All right, next one we're going to do is right Riemann sums. So in this one, I pick the right value on the interval. So this time, I would be picking this value for the first interval. So we're going to be over approximating every time for this one. So just straight across there like that. So yeah, look at all that over approximation. Like we're using the right value every time, which in the first one would be the height of 2, and the height of 3, and the height of 4. And so our first interval, it's 3 wide, just like the last one, but instead it's a height of 2, and so that area is 6. In our second interval, the width is still 5, but now the height, I'm picking the higher value, which is 3. And the third one, my height is 4 on that interval, because I'm picking the right value over here. And I multiply that by 7, so I get 15 and 28 for these areas. And I add them all up, I get 21 plus 28 is 49 units squared. Definitely over approximate, or at least it's more than this one. And this number is between these, which shows that trapezoidal sums, given similar intervals, will tend to be more accurate. Alright, let's do midpoint now. Oh, before we do that, the left and right Riemann sums, I said there were 5 ways, left, right, midpoint, over approximation and under approximation. In this case, our left Riemann sum ended up being an under approximation. It isn't always. Like sometimes the left Riemann sum will be an over approximation. It just kind of depends on what the graph looks like. But this is an example of under approximating where we always picked the lower side. This is an example of over approximating where we always picked the bigger side. So yeah, we already knocked out 4 of these, as it were. So let's do midpoint sums now. And this time I'm going to do it right. You can see take 1 here. Okay, so we need to know our equation for midpoint sums. This equation is pretty easy to figure out. The square root of x is equal to y. Because the height is always the square root, it's just square root function. So we can figure out the midpoints of 1 and 4 here is 2.5. We're going to plug that into our formula here. We're going to figure out that y value, and that's going to be our height on that first interval. So I'm going to plug in 2.5 and get square root of 2.5. And so that is my first height on this first interval. And so I multiply square root of 2.5 times 3. On the second interval, my midpoint between 4 and 9 is 4 plus 9 divided by 2. 13 divided by 2 is 6.5. So 6.5 is the midpoint there. And so I'm going to get the square root of 6.5 as my height. And I'm going to multiply by 5 because that's the width of the box. My third midpoint, I'm going to find the midpoint between 9 and 16. 9 plus 16 is 25, divided by 2 is 12.5. So square root of 12.5 is that answer, times 7. And now I gotta figure these all out, and I do not have those square roots memorized. So here we go. This first one is 4.743. The second one is 12.748. And the third one I did it wrong. Sad panda. All right, is 24.749. We add all these together, and we get 42.24. Or 240 actually. Cool. 3 decimal places is the general AP thing, so that's what I like to do when I do these examples. Okay, so time to see which one of these is the best approximation. So let's actually take the integral of x to the 1/2. So our function was y equals root x. So let's take the integral of root x. So I'm going to zoom down here. And we're going to take the integral of root x from 1 to 16. Just see what we get here. So this is x to the 1/2. So when we take the integral, we're going to get x to the 3/2 divided by 3/2. And we're plugging in 1 and 16. So this is going to be 2/3 16 to the 3/2 minus 2/3 1 to the 3/2. 16 to the 3/2 is the square root of 16, which is 4, cubed. So it's actually 64, because 4 cubed is 64. So this is actually 128 over 3 minus, well, this is 1 to the 3/2 is just 1, minus 2/3. So that's 126 over 3. And that's actually 42. So which one of ours was the most accurate? Well, it sure as heck wasn't either of these two. However, if we go directly in between these two, 15, 7.5, add 7.5 to that, 41.5, that's not too bad. It's the same as this one, but this one's actually our best. So the midpoint one worked out the best this case. It won't always be the same one working out the best, just as a nature of how these work. So yeah, that's it for this section.